Ted received his PhD from MIT in 2018, and he's been a research staff member in the quantum computing theory group at IBM and the TJ Watson Research Center since then. His current interests include quantum algorithms, particularly those for small quantum computers, and quantum error correction with a focus on new error correcting codes and architectural considerations for their practical use. Today, Ted will be talking to us about exotic surface codes. So go ahead, Ted. Thank you.
Okay, thanks, Andrew, and thanks, everyone. So I think you can see my PowerPoint right now. Feel free to ask questions as we go along. Yeah, I mean, I realize the audience might be somewhat diverse here, so I want everyone to be on the same page and keep up. Right, so this, I mean, I guess I titled it Exotic Surface Codes for this seminar, but I've given this talk a couple times before, and the title of the archive paper is A Graph-Based Formalism for Surface Codes and Twists. Okay. So essentially, we're looking at a bunch of different surface codes here in the literature, and we're going to try to unify them into one model. And then hopefully from our unification, we get new surface codes. I mean, in fact, we found some new examples. So I guess like the first surface code was this Brabi-Kitaev in 1998. And that was on, well, it was in the plane as opposed to Kitaev's surface code on the torus, or perhaps you would call that the toric code. Bombin and Delgado rotated the Brabi-Kitaev lattice so that they could use fewer qubits to encode still one logical qubit. And then there were a series of papers about certain defects in the surface code called twist defects. So I guess Bombin was the first sort of in parallel with Kitaev to define these twist defects. And in his formulation here, 2010, there are weight 5 faces in the graph, and these are essentially where your twist defects are located. So somewhat later, me, along with Isaac Kim, created this triangular surface code. And this effectively has a twist defect in the middle here, although it differs, qualitatively from Bombin's code because there are no weight 5 stabilizers. And then this idea of twist defects also takes different forms, even as in the Krishna-Palan formalism or the Kessel ring stellated codes, which are sort of a generalization of this triangle code. So essentially, like, there's this variety of models in the literature, and we want to describe them all in the same formalism and understand where these twist defects come from. Okay, so why do that? Well, first, I mean, it's just sort of conceptually nice to do that. But something I think the center here could probably appreciate is that this organizes the search for better code, so you can get better code parameters. So here, n is the number of physical qubits you're using, k is the number of encoded qubits, and then d is a measure of the code performance. It's the code distance. And there's this Brabi-Bullen-Turhal bound, which says that in 2 dimensions, you can't really do better than n equals, or n being proportional to kd squared, but you can improve that constant c. So if we have some formalism for surface codes, we can actually search through this formalism, search through the codes for better constant c. Also, we can start to classify these codes in terms of topological phases or like the topology of logical operators. We'll see, for instance, that the twist defects are essentially between the twist defects, you get a logical operator. So the distance between twist defects sort of determines the code distance. And then finally, you can relate codes, different codes in the model, by transforming one to the other, perhaps through what are called Bachner moves. And then what are some practical consequences? So here I'm hoping to spur a little bit of discussion in the center here, because one of the results of our work here is saying what amount of savings you can get by using different topologies or different graphs. And so if I tell you that you can use half as many qubits to encode the same number of logical qubits by putting some code on the torus, is that really worth the engineering to you? So here is some picture where maybe the connections are in 2 different layers, and the connections can cross each other as long as they're in different layers. And using this construction, you could effectively implement a torus and improve your code rate by a factor of 2. Right. So I guess let's go a little bit deeper into this problem here. So some of the codes that I'm going to be talking about are on higher genus surfaces, such as a torus, a double torus. Sometimes they're on non-orientable surfaces as well. But in the lab, we perhaps just have qubits on a chip, which is topologically a disk. So the question is, how do we actually implement these higher genus surfaces? And I guess there are a couple options that I'll talk about. And I mean, these are the ones that occurred to me immediately. I mean, maybe there's option 3 or 4 or whatever, but I'll talk about 2 options. So option 1 is that you have just a few long-range connections. And so this is just order L. So it's proportional to the perimeter, not proportional to the bulk, which would be L squared. So this is essentially what I showed on the previous slide, that you just connect one edge to the other edge using some of these long range connections. So yeah, so I sort of want to probe the center, like how easy would this be to implement, and is this something that you would be interested in thinking about? So it's not just for implementing the codes that I'm talking about here, though. So this capability might also be important to connect different chips and fridges as part of a large-scale quantum computer anyway. So just as a stepping stone, you can implement some of these higher genus codes, but then also connect up your quantum computer eventually. And you also, if you're able to implement these long-range connections and do so somewhat reliably, then that will be an important part of implementing even more powerful quantum codes, such as the fascinating quantum LDPC codes that have been recently proposed that are achieving very good code distances and very good code rates. Now, option 2 for implementing these higher genus surfaces is, instead of the long-range connections, you can have many intricate short-range connections. So let's take the torus case as an example here. So you can fold, well, obviously you start with this square and you identify opposite sides. That's a torus. Now you can fold that up first along the vertical here, and then along the horizontal. And now, for instance, if you had a single toric code stabilizer per face, now you have 4, right? Because now there are 4 layers. So at every vertex in this folded graph, you have 4 qubits, and then you also have 4 ancilla qubits on the faces to measure the 4 stabilizers. And of course, this requires more complicated connections, some of which are drawn here lightly in yellow. Yeah, so I mean, I also don't have a great understanding of how easy that would be. But at least these are somewhat local. I mean, they're not stretching all the way across the lattice. They're just, yeah, I mean, they're just a constant distance away. And there are some optimizations to be made here if you're willing to trade off the how well the error correcting code works for less connectivity. For instance, you could get rid of a lot of the ancilla qubits that are measuring the stabilizers and just use one per face, which now has to do 4 times the work. It has to measure all 4 stabilizers, which increases the circuit depth and I expect lowers the threshold. So some study would have to be done to investigate how much and whether the advantages we get from less connectivity actually are worth it. Right, so then, I mean, this was option 2A in the sense that it was this folding procedure, but perhaps more generally, you could just imagine flattening the torus or your hygienist surface so that now there are 2 layers effectively. So now there are 2 qubits per site and maybe 2 ancillas on the face. And you could do this on the higher genus torus as well. Just flatten it down, squashing a donut or a double donut. And then, again, you end up with the situation where you need some intricate short range connections. Now, again, you can possibly reduce the connectivity, which leads to deeper circuits and lower thresholds. And again, there's some advantage for implementing this connectivity beyond implementing the codes that I'm talking about here. Like perhaps you can improve your implementation of color codes or even logical gates on the codes if you're able to implement these short range intricate connections. Okay, so yeah, so that was my discussion of some of the practical details here, which I hope that the center will sort of latch on to and stimulate some discussion. Okay, so back to the practical consequences here. So I went on a long rant there about connectivity. I think that's the most interesting question. But then also, there's this question of what logical gates are easy. So perhaps we can find codes where we make some subset of the Clifford gates easy in the sense that logical operators are accessible on the boundary of the patches. So we can use ancilla patches to do logical C0s or even like Hadamard's or S gates. And then you can also do some Clifford gates by moving the twist defects around. So you might want to also leave enough space to move them around each other. You sort of have to keep them far apart as well to make sure that the code distance doesn't get reduced during this process. And then finally, one consequence of our work might be the discovery of better decoders. Because especially when there are twist defects in the code, the decoding problem becomes a little bit more complicated. So we have some ideas to improve decoding of correlated errors. Okay, so yeah, now I'm gonna get into the more technical details of our construction. So basically the outline of the construction is that we have some graph embedded onto a 2D manifold. And using that graph, we're going to place qubits and place stabilizers, and that will define our code. Now in the paper, I go through this Majorana surface code construction, and from that get to the qubit surface code. But there's also a more direct way using what are called cyclically anti-commuting sets, or lists, I think I call it later, of polys. So that's what I'm going to do in this talk. I'm not going to talk about the Majorana surface codes at all. Now also importance properties of these codes can be described in terms of properties of the embedded graph. So for instance, we have a formula for the number of encoded qubits, and we also have some bounds in the distance. And then between those two, I'm going to give a lot of examples, which I think is probably the coolest part of the talk, just to, see some pictures. Okay. Now, because this is a somewhat more diverse audience, I'll just briefly describe what stabilizer codes are. So you have the signless polys, which are just tensor products of I, X, Y, and Z. And then if you put plus minus one, plus minus I signs on them, you get the poly group. Now the stabilizer group, which defines your code, is a subgroup of that poly group, and it can't contain minus identity. That's the only constraint. This implies that the stabilizer group is abelian, actually, because if it were not, then it would include minus I, which it's not allowed to. So now the code space is defined as the simultaneous +1 eigenspace of all the stabilizers. And it turns out that the code space always has dimension that's a power of 2, and it will encode k qubits if its dimension is 2k. Now, how can you envision this code space? Well, the code space is a subspace of the n-qubit Hilbert space. And when errors happen, it will move you to an orthogonal space. And you can therefore identify these errors by measuring some generating set of the stabilizer. And you will see that some of the stabilizers are in the mind. Some are going to return -1 rather than +1, which you would expect if you were in the code space. So in this way, you can identify the error. So when I define my codes, I will just be specifying a generating set of the stabilizer S. Now, errors that commute with S entirely are not detectable. And if you commute with S entirely and you're also not in S, then you're a logical operator. And the minimum weight of such logical operators defines the code distance. Okay, so that's my very brief introduction here. Now we're also going to be just focused on local stabilizer codes, and in particular, codes that are local in 2 dimensions. So in this case, there's some like code family where there's some parameter n, which is the total number of qubits that you can increase arbitrarily. Usually n is, we have like an L by L patch or something. So n is L squared, and we can increase L arbitrarily. So for the 2-dimensional code families, what makes it 2-dimensional is the fact that you have some qubits sort of spread out with even density on a 2D manifold, and the stabilizers are always constrained to constant sized regions, which means that they act on a constant number of qubits, And it means also that every qubit is acted on by a constant number of stabilizer generators as well. Okay. So also, I mean, our codes are a little bit more structured than just like throwing the qubits out there on the 2D manifold. We actually, use a 2D embedded graph to describe where to place the qubits. So what is a 2D embedded graph? Well, it's really just, I mean, you draw the graph. You're able to draw the graph on the surface without the edges crossing, right? So if you have genus 0, or also called planar graphs, these are graphs that you can draw on the sphere without the edges crossing, such as the rotated surface code graph on the left. And then there's also, I mean, you can draw these on higher genus surfaces as well, often conveniently drawn by having some polygon with opposite edges, or they don't necessarily have to be opposite edges, just edges identified, and then the graph drawn, such as in this example, where there's just a square lattice on the torus, and this defines some sort of toric code. I'll tell you where to place the qubits in the stabilizers next. Okay. So once we have the graph, I mean, here I'm just showing part of a graph. You place m-2 over 2 qubits at a degree m vertex. Okay, so this is, well, this is in the case that the vertex degree is even. In the case that the vertex degree is odd, you place m-1 over 2. Sorry, I guess I didn't write that. Right. So in the example on the right, let's just make sure that this is understandable. There's a degree 4 vertex down here. You can see my cursor. And at degree 4 vertices, we place a single qubit. At degree 3 vertices, we also place a single qubit. But then when you go to degree 5 or degree 6, you place 2 qubits. Degree 7 or degree 8, you would place 3, etc. Okay. Now I have to tell you how to define the stabilizers. So around each of these vertices, you write polys, and these polys form a certain, well, they form certain commutation relations with each other. In particular, they should be a cyclically anti-commuting list of polys. So this means that, well, it's a list of polys. The first and last elements are considered adjacent. And then adjacent polys in the list should anti-commute, but every other pair of polys should commute. So what are some simple examples? If you have a cyclically anti-commuting list of length 3, we could write that as X, Y, and Z, right? So every poly anti-commutes with its neighbors. If we have a cyclically anti-commuting list of length 4, that an example could be X, Z, X, Z. So you anti-commute with your neighbors, but you also commute with elements of the list that are not your neighbor. So Z commutes with Z, obviously, and X commutes with X. Okay, so the code construction then goes, we place the qubits at the vertices, and then we write a cyclically anti-commuting list of polys around each vertex. And the product of polys within a face is a stabilizer. So for instance, in the example on the right here, the stabilizer corresponding to the face is like poly Y applied to the qubit on the left, poly X applied to the qubits on the bottom, IY applied to the 2 qubits at the degree 5 vertex, and ZZ applied to the 2 qubits at the degree 6 vertex. And this is similar to this label set in this paper by Jonas Anderson. but I think he just considers degree 3 and 4 vertices. Okay, so how do we actually construct cyclically anti-commuting lists? Like, do they exist? Something you might be wondering. So we already did so for lengths 3 and 4. But for higher lengths, you can actually just concatenate these lengths 3 and 4 in a specific way. So if we have a length 7 cyclically anti-commuting list, or we want a length 7, I should say, then we can concatenate 2 length 4s and a single length 3 cyclically anti-commuting list, as shown on the right here, the right side of the arrow. So here, I mean, we have 3 qubits because it's a degree 7 vertex. There are 3 qubits there. Then we write, length 4 or length 3 cyclically anti-commuting lists around each vertex in this like expanded construction, and then the polys are associated to like the sectors in this expanded construction. So P0 would just be a single X applied to the first qubit. P1 would be ZZ applied to the first 2 qubits. P2 XX applied to the last 2. P3 poly Y applied to the last qubit, and so on. And you can show that this always makes a cyclically anti-commuting list. So for instance, if we wanted a length 8-1, then we would just use the length 4 cyclically anti-commuting list as our base. We would never need a length 3 here. Okay, so I hope that convinces you that these exist, or yeah, I mean, eventually it will convince you. Okay, so now I'll talk about how many encoded qubits there are in these surface codes. And this ends up being pretty interesting because it relates to a certain graph property. So the theorem is that a surface code on the genus G manifold with m odd degree vertices encodes, well, this many logical qubits. So it depends on both the genus, 2 times G if it's orientable, or G if it's non-orientable. And then also this property of checkerboardability. So if the graph is checkerboardable, then then you get an extra 0 term. But if it's not checkerboardable, then you get m-2/2, where m is the number of odd degree vertices. This checkerboardability property is just that the graph's faces can be 2-colored, such that adjacent faces are colored differently. I hope that the name implies what it is. We'll see some examples next. So if a graph actually has odd degree vertices, then it is not checkerboardable, because locally around that odd degree vertex, you can't even 2-color the faces. So the proof of this theorem essentially amounts to counting where the number of encoded qubits is n minus the number of independent stabilizer generators, and then you can count up the number of independent stabilizer generators. It just turns out to be the number of faces -1 if the graph is not checkerboardable. You get the -1 because the product of all the faces ends up being identity, and it's f-2 if it is checkerboardable, because if it's checkerboardable, then the product of either color of face, for instance, all the white faces, is also going to be identity. Right. So okay, let's look at some examples here. Both of these, the example on the left is not checkerboardable. Why is that? I mean, it kind of looks like it should be. So I've colored the faces black or white, But then there's also, because this is embedded on the sphere, there's also the outer face, which I don't know how to color because it's adjacent to both black and white faces. And no matter how you try to color this, you'll not get a checkerboardable color. So this graph ends up being not checkerboardable. It has genus 0. So how many encoded qubits does it encode? M is also 4, because M is the number of odd degree vertices, and there's an odd degree vertex at each corner. So the number of encoded qubits is just 1. And this should be consistent with our, this is consistent with our understanding of the rotated surface code, which is what the picture is. Now, if we were to put a square lattice on the torus, it depends a little bit on the lattice dimension, or the lattice like spacing. But in this example on the right here, this graph is checkerboardable, and there is a checkerboardable coloring shown. Now the genus is 1. This is a torus, so this encodes 2 logical qubits. We can also put square lattices on the torus that are not checkerboardable. In this case, it's like a 3x3 lattice. And so if I start trying to color the faces, I can start by coloring a face black, and then adjacent faces white, and then this one has to be black. But then I get to the question mark faces, and I don't know how to color those consistently. So this ends up being not checkerboardable, and therefore you lose one of the logical qubits. At least if you're comparing with this example, you lose one of the logical qubits because there are no odd degree vertices. M is equal to 0. So you get the second term here, which evaluates the -1. Right, so even if it's not checkerboardable, sometimes we put a coloring on it, and we say that there are defect lines. So these are these stitched edges. And if there's a stitched edge, it means that the adjacent faces in the particular coloring are colored the same. So they're sort of illegitimately colored. And these defect lines turn out to be important in identifying logical operators. So, okay, so now we'll go through some examples of interesting codes. Maybe I should pause. I haven't paused in a while. Hopefully there aren't. Well, are there questions? Maybe not. I guess I would see some sort of, okay. Yeah, please interrupt me if there are questions. Right, so the first example here is a family of cyclic Tor codes. And these all parameterized by relatively prime integers, A and B. And the idea is that you draw these lines, y equals b over a times x, and y equals minus a over b times x. On this square with opposite sides identified. So for instance, in the case A and B equals 1 and 2, you draw a line with slope 2. Eventually it hits the edge of the square and it comes back around. And you draw the line with slope -1/2. And eventually that hits the edge and comes back around. And this will make some graph on the torus for you. Now, how many? Oh, okay. We can also write cyclically anti-commuting lists around each face, and you can see that the stabilizers are weight 4 associated to each face here, and they take the form like xz, zx. Oh. Oh, I guess okay, sure. I talked about the parameters here. So in general, the parameters of these codes are, well, the number of qubits is a squared plus b squared. And then if n is odd, there's one logical qubit and the distance is a plus b. And if n is even, there are two logical qubits and the distance is max a and b. So you can actually achieve n equals 1/2 kd squared in two different regimes, when a equals b minus 1 or when a equals 1 and b is odd. And some of these codes have appeared before. What I found really interesting about these codes is that the 5-qubit code, the smallest error correcting quantum code, is actually part of this family. So the 5-qubit code is essentially a topological code, which was a bit of a surprise to me.
Can I think I didn't catch something basic.
Yeah.
So these cyclically anti-commuting strings.
Right.
Do you enforce that constraint? Does that, I mean, where is it important? Is it because it makes the stabilizers on different faces commute, or
Yeah,
I missed that key
exactly.
point.
Yeah, I guess I didn't talk about that, but yes. So it makes the stabilizers on, it makes all the stabilizers commute, because stabilizers are associated to faces, and faces will like sort of touch along an edge, which anti-commutes at the two places. Yeah, the fact that it's cyclically anti-commuting is also important for strings of logical operators to sort of traverse the code. So therefore you get distance that's extensive in the code size.
Thanks.
As we'll see later. Yeah. Yep, good question. Right, so that was an example to get our feet wet. And then I wanted to take a brief aside here and talk about the relation to Kitaev's model. Where so in Kitaev's model of surface codes, you also have an embedded graph on a 2D manifold, and you place qubits on the edges of the graph rather than the vertices like we did. And so, and then you define two types of stabilizers. You define the X-type stabilizers around the vertices, for instance, and the Z-type stabilizers around the faces. So if we were to write one of Kitaev's codes in our model, we would, well, we'd start with Kitaev's embedded graph, but then we'd associate qubits to edges, and then we would write down this medial graph, where so the point of the medial graph is that now the qubits are on the vertices of the medial graph. So the medial graph, the code defined using the medial graph in our model is the same code as Kitaev's code defined using, in this case, the light gray graph, the original graph with Kitaev's model. So this is an example in the projected plane. Now, if you go through this process, you'll realize that medial graphs are always checkerboardable, and that medial graphs are always four regular. So if you're defining codes using Kitaev's model, then you get a subset of the codes that are defined in our model. And there are also similar observations about medial graphs made in these papers. Right, so continuing with some examples, I want to talk a little bit about these stellated codes. So we saw examples very early on in the talk where there's this, well, I called it the triangular surface code. Sort of unclear why it's triangular, but there is like threefold symmetry about the center. And earlier in the talk, this was just in the plane, but now we can also put it on the torus. So the idea here is that you can represent the torus by a square with opposite sides identified, but you can also represent it with a hexagon with opposite sides identified. And to convince yourself of this, you have to go through some Euler's formula, just to make sure that the count of edges, vertices, and faces goes as it should. But these both represent the torus. And the idea is that we can take this code with threefold symmetry, and we can also identify opposite edges here, just as done on the hexagon. And you end up with a triangle code on the torus, and this code encodes twice as many logical qubits as the code did in the plane, and it uses slightly fewer physical qubits, and the distance doesn't get reduced that much. So generally, the distance is going to get reduced by 1. The number of qubits that you use is going to get reduced only by the perimeter, and the number of logical qubits is going to double. Right, so then you can do this also for larger stellated codes, such as this one with 5-fold symmetry. And this one you have to place on the double torus. And again, you double the number of encoded qubits with small changes to the number of physical qubits and the code distance. Right, so here's the general statement is that as you increase the amount of symmetry, you can approach n equals 1/4 kd squared. And this is to be compared against the stellated codes in the plane, which achieve 1/2 kd squared. Smaller constant is better because fewer number of physical qubits we use, the better. Right, so then the third example here, again, sort of starts with the triangle code, this 3-fold symmetry code in the plane, which achieves 3/4 kd squared. Right, so this is the graph. The stars are supposed to indicate these odd degree vertices, which can also be called the twist defects. And then I abstract away there's a lot of lattice there that we can just imagine it being there. You choose the lattice spacing to be dense enough that you achieve the code distance that you want. And so now you can extend the patch. Again, the stars are supposed to represent these odd degree vertices. And so with this first extension, you encode an additional logical qubit, and now n equals 5/8 kd squared. So we're actually improving this constant, reducing the constant as we extend, and so on. Now 3 logical qubits, 4 logical qubits, and eventually you approach 1/2 kd squared, which is a similar constant to what they get. Well, actually the same constant as what they get in this Hastings-Geller paper. So I call this the planar packing code because you're packing these twist defects as close as you can in the plane, sort of signified by this circle packing that's going on in the background of this picture. And then finally, we use our construction to create new hyperbolic codes. Okay, so this, maybe I won't go through this too much, but there is a way to sort of systematically create hyperbolic codes by finding normal subgroups of certain free groups. And essentially what the group, the elements of this group represent are reflections of these triangular regions of surface about various directions. So Yeah, so in this way you describe regular graphs. Where by regular I mean that the degree of every vertex is the same, and that the degree of every face, or the number of sides that every face has, is the same. So in this case, every face is a pentagon, and every vertex is degree 4. And so one normal subgroup of this 5-4 free group is defined by these relations. Rho tau rho lambda to the 4th and rho lambda tau to the 5th equals 1. And that defines this code that I've drawn here. So this is a graph on some high genus surface, and the labels of the edges are telling you that the edges are identified. And if there's a prime, that means the edges are identified non-orientably. Right, so this is a non-orientable surface. And so we can go through this finding of normal subgroups and come up with some very small hyperbolic codes. So for instance, the one shown in the picture here was 25-4. It uses 20 qubits and got 5 qubits with distance 4. Okay, so I have like 10 minutes or so. So I can discuss the where the logical operators of the codes are, and talk about the code distance. So to figure out the code distance, well, I mean, we should identify where logical operators are, because the code distance is the weight of the smallest logical operator, the Pauli weight. And to do that, we'll define this, what's called a decoding graph. So decoding graph has a vertex for every face in the original graph. And then you connect these vertices as shown here. So around degree 3 vertices, well, there's sort of this triangular connection. Around degree 4, you connect opposite vertices. Around degree 5, you connect everything. Around degree 6, you connect every other vertex. So in general, around even degree vertices, you connect every other vertex, and around odd degree, you connect everything. So the idea here is that the edges are representing Paulis that anti-commute with exactly 2 faces. And so this is, the fact that the decoding graph looks like this around the vertices is a consequence of our enforcement of the cyclically anti-commuting list that defines our stabilizers. And then also, whatever Pauli you choose to apply to the qubits at a vertex can be represented by some subset of these edges, essentially the product of those subsets, or the product of those edges. So what are some examples? So here,
Sorry, Ted, can I interrupt again?
Yeah.
So when you said Pauli that anti-commutes with exactly 2 faces, do you mean like the product of all the Pauli strings that are on that edge or that face? Or
right. So when we write down the cyclically anti-commuting list, there is a Pauli associated to each face around the vertex. And then there exists a Pauli that anti-commutes with 2 of those Paulis in the cyclically anti-commuting list.
oh, so it's just the ones that are in that corner that the triangle is surrounding, and
yeah, that's right. So the Pauli associated
not the entire face. Okay.
The Pauli associated to this edge anti-commutes with the
yeah. Thank you.
With the elements of the cyclically anti-commuting list corresponding to this face and this face. Okay, so here's a decoding graph example. We have the large graph is drawn with the dark lines, and then some example edges of the decoding graph are drawn in green, red, and blue. I think right, so the stabilizers are, some examples are A, B, and C, the green. Now these are cycles in the decoding graph. So why are they cycles? Well, obviously B and C are, because they're closed like this, but also A is a cycle because we associate a single vertex in the decoding graph to the outer face. So, I just didn't draw this closed, but like both ends terminate on the outer face. Now, well, likewise with E and F, those are closed cycles and they terminate on the outer face. But these E and F turn out to be logical operators, and you can see that because E and F, the polys that E and F represent actually anti-commute, and they anti-commute because E and F cross at this one site here, right? And now cycle D goes around these odd degree vertices, and it turns out that cycle D is actually equivalent to the logical operator of cycle E. And you can see that because cycle D anti-commutes with cycle F just as cycle E does. And there's also only one logical qubit for this code. All that aside, so the general statement is that the centralizer of the stabilizer group is represented by cycles in this decoding graph. So we have the stabilizer cycles and also all the logical operators represented by cycles in the decoding graph. So the decoding graph is really important for identifying the logical operators. In the checkerboardable case, which the previous example was not, the decoding graph has two connected components, both embedding in the same manifold as the original graph. And then we can make the statement that non-trivial logical operators are actually homologically non-trivial cycles in the decoding graph. The non-checkerboardable case is more interesting. So in the non-checkerboardable case, the decoding graph does not necessarily embed in the same manifold as the original graph. This is because essentially you can, well, I mean, in the checkerboardable case, there are two separate connected components. These correspond to the different face colors. So the one connected component will have vertices associated only to the black faces, for instance, and the other will have vertices associated with white faces. And you can't cross from one connected component to the other. But in the non-checkerboardable case, you can cross between those components, and therefore at vertices, you will have edges crossing, at least in how I've drawn the decoding graph. So the decoding graph does not necessarily embed in the same manifold. So to get around this, we define this doubled graph. And the idea of the doubled graph is that the decoding graph of it is isomorphic to the original decoding graph, but it actually embeds in some potentially higher genus surface. Right, so if G represents a surface code encoding K qubits, and G is orientable, then G squared is orientable with genus K. If G is non-orientable, then G squared is either orientable with genus K or non-orientable with genus 2K. So the genus may increase. Now here's some very simple example of the doubled graph. Essentially, the idea of the doubled graph is that every time you cross one of these defect lines, you'll move to a different copy of the code. So here in the tort code case, we have an odd by even square lattice. There's a single defect line, rubber band around one of the around the torus here, and you can cut it apart there. And now take two copies that we both cut apart and glue them together at the cut seams. And this is how you'll form the double graph G squared. In this case, it ends up being a torus again, because you cut the torus apart and then you glued two segments together. But if it were a higher genus surface and the defect lines were placed appropriately, then this might be a higher genus surface. So that's what this example would go through, but I don't really want to go through it right here. So I mean, you cut along these, along every defect line, you take two copies, you join them together, and then you identify edges appropriately. And you started with a genus 3 orientable manifold, I believe, or non-orientable. Genus 3 non-orientable, and you end up with a genus 6 non-orientable. Now you can actually make this doubled graph for familiar codes, for like the rotated toric code, which is non-checkerboardable, remember, because the outer face could not be colored. You can embed this also in the torus. This is the torus because it's a hexagon with opposite sides identified. And there are essentially two copies of the code. And one of the properties of the doubled graph is that it's always checkerboardable. And so I'm showing the checkerboarding here. And the logical operators of the original code are homologically non-trivial cycles in the decoding graph, shown here in red and green. So this is a way to figure out the logical operators in the non-checkerboardable case and relate them to homological non-triviality. And then you can also make the double graph with the triangular surface code. It looks kind of crazy. It looks like this. Right, so we can use the doubled graph to place bounds on the code distance. If the graph is checkerboardable, it turns out that the distance is, well, I mean, you don't need to do the doubled graph in the checkerboardable case. The distance is just the combinatorial systole of the decoding graph. But if the graph is not checkerboardable, then you should look at the systole of the doubled graph. And there are some bounds in this case. We would like to, figure out how to calculate the distance exactly, but that is still an open question. Okay, so that's, I conclude where I started. So we talked about the embedded graphs, we talked about defining qubit surface codes, and then we talked about the code parameters and we showed some examples. You can see the archive paper here, and I'm happy to answer any other questions. Thank you.
Wonderful. Thanks a lot, Ted. So do we have any questions from the audience? All right, so well, to get things started then, Ted, I've got a question. I mean, the construction, at least the way you're laying it out over here, seems somewhat, at least it's presented as somewhat married to the notion of embedding in a 2D manifold. So how would things change if you wanted to instead do 3D, or, if you're thinking some of the crazier stuff like Ben Brown's thinking about, maybe even 4?
Yeah, so that things get much more complicated. This is a question that we get a lot. Yeah, so I mean, in 2 dimensions, it seems like every every surface code can be sort of unified in this framework, but in 3 dimensions and higher, there's just a lot more that's going on. And like, it doesn't seem to me like it's going to unify in such a nice way. I mean, this is kind of related to the proofs of like topological order that Bombin and Zhang Ha have formalized.
Okay, any other, yeah. Go ahead.
Yeah, I'll ask a question or make a comment or something. So thanks, Ted. It was really cool talk. And I'm gonna have to do some more homework to be able to catch up from the hardware side to all these codes and things. In the beginning, you were sort of asking, what are the connections in the center, and is it possible to do long range connections or other sorts of things like that? I think the answer is definitely yes, it's possible to do those things. Yes, we're interested in exploring them. One of the themes of the C2QA is also looking at modularity and different kinds of architectures and things like that. A thing that would be useful, maybe one reason I think why people make chips with nearest neighbor connections is like, well, that's the easier thing to do and also gives probably higher performance. So an interesting question would be like, for adding some long range connections, does it matter what their performance is? Is it okay if they are lower bandwidth? That is, with the gates are slower typically in a hard, if you go for those longer range, they might be slower gates or lower performance. So would that then be the bottleneck, or is there a way to kind of, still benefit from some? And when would we know, let's say in an actual hardware platform, when is the time to think carefully about that? This would be really useful to kind of inform these discussions a bit more, to get quantitative about like the performance trade-offs in these things.
Yeah, I agree for sure. So that would require some simulations of these codes, which should be able to be done. Like maybe we can say the long range gates, fail with twice the error rate or something, and just see if the advantages of the code, the fact that you get like twice the number of encoded qubits, can really can tolerate that sort of noise. Like maybe you'll have to make the code bigger just to correct the higher noise rate.
Right. So maybe to turn it into a more concrete question, what would you need to know from the hardware side in order to be able to make some of those estimates? Or who would be the right people to have in a room to at least begin batting that stuff around?
Right. Yeah, I think it's the error rate. Now, well, I guess also the time that the gate takes might be important as well, because perhaps we're doing fewer cycles of measurement for the stabilizers that span this boundary. Even if we can continue measuring the other stabilizers quickly. So probably the time and error rates of these long range gates.
So one of the questions I guess I have regarding that is, if imagine we're dealing again with something like the toric code, right, where we've got the long range connections only in the boundary, as opposed to over the entire volume. I guess the question is, intuitively, do you imagine that you would be able to get be able to get by with higher error rates on the less numerous gates on the boundary than in the more numerous ones in the volume?
Yeah, I think that's a reasonable assumption. Yeah.
Probably you need numerical simulation in order to really get it, but I just wanted to see.
My intuition would be yes.
Yeah. But so,
That's encouraging,
but
at
going back
least.
to the other question, yeah, do you have any idea about people who would be kind of neat to talk to within the center that we could potentially bring together to look at trying to make this real?
Well, people with knowledge about these long range operations, maybe they can volunteer. I'm not necessarily sure.
Yeah, fair enough.
I mean, perhaps Rob knows the specific names, or Steve.
Great. So another question I guess I had, which is a little, again, it might be totally naive, so I apologize.
Mhm.
But the question I guess I have is with this, translation that you were doing that, basically ended up like roughly doubling the number, or actually exactly doubling the number of logical qubits that you end up getting. What ends up happening to the transversal operations when you do this transformation? Are they the same, or could they be different?
Right. So I think what you're referencing is maybe the stellated codes when I'm embedding them on higher genus surfaces. So they don't actually have any they don't have any strictly transversal operations. There is a transversal operation that requires permuting some of the qubits in the code, or rotating it. I believe that operation should, well, it's a good question. I mean, I haven't thought about it specifically, but I think that operation might still exist, that transversal operation, because the code still has the symmetry. Now, I mean, when it's encoded in the plane, what is convenient is that the logical operators are sort of on the boundary of the patch. And this means that you can introduce some ancilla patches and do some lattice surgery to do logical gates. But now when it's in the higher genus surface, it's a little bit unclear how you would do such lattice surgery. So that is a good question, and a disadvantage maybe of going to the higher genus case.
Cool. All right. Any other questions for Ted, or ideas, or anything?
So coming from more of a solid state physics background, some of the codes that you showed sort of remind me of like quasi-crystals, for instance. And I'm wondering if the theory of those systems could be useful in this context at all.
I haven't thought about that. Yeah, I mean, that's a good recommendation. Maybe I should look at some quasi-crystal literature, or maybe you could point me towards some.
Yeah, I wonder if there's any connection between those ideas and some of these fractal codes that I ended up seeing a while back.
Right.
Who was that again? Was it Benny Yoshida?
Right. So there are, I think these are classical codes in 2 dimensions, which the logical operators end up looking well, fractal-like. Yeah, but those are classical codes, and then there's also quantum codes that are fractal-like in 3 dimensions, such as the Haas qubit code. So definitely more exotic quantum behavior in higher dimensions, as your first question pointed to.
So I guess I've got another kind of like broader or weirder question in a way, right? Like if we're considering some of the work that we're doing in this center is involving, you know, microwave modes coupled to qubits, right? So if we're storing a lot of our information in the microwave modes, we don't really kind of have, strong limitations on the connectivity in a direct way. We've got cutoffs that end up coming in, but we don't really have, you can sort of think of it as being sort of all to all. So I guess a question that I've got kind of more broadly is, could we have some advantages for implementing small codes in this sort of a setting, where if we don't need to necessarily worry about connectivity as strongly?
Yeah, I mean, that's a good question. So then we're not actually limited to 2D in any way.
The cutoff, I think, will probably still create some
Right.
limits to how far we could scale this up.
Right.
But, and I need to think a little bit more about what the reasonable computational model that we'd have to assume for doing essentially the stabilizer measurements in that space. But there could be some interesting ways that we can get around some hardware connectivity issues by going to these microwave modes.
Right. I wonder if that would be a reasonable way to implement, what option 2 in the beginning of my talk, where they're intricate sort of short range connectivity, which you can use to effectively implement these higher genus codes.
Yeah, I think maybe what Nathan was driving at is you could encode all of those small sets of qubits in one oscillator. Is that what you meant,
Yeah.
Nathan?
Yeah.
In principle.
Yeah.
I mean, in principle, you can cram a lot into an infinite dimensional space.
Yeah.
They have very correlated errors in some form. So
the very correlated errors might be problematic for fault tolerance if
I get to work on that.
yeah.
But that of course is also an interesting thing, because there may be forms of twirling or a dynamical decoupling that could be used to limit those problems. But in any case, yeah, it'd be good to get an idea about what some of these numbers are, so that way we could consider what the trade-offs might be.
Yeah. Yeah, and again, I think like thinking about these intricate short range connections or long range connections, has advantages not only for implementing the codes that I talked about, but is going to have advantages for small algorithms or eventually, better codes or such as these LDPC codes. So I think like generally the message is that like any additional connectivity you can give is probably going to help.
Right. But if you do this origami thing and fold them up,
Yeah.
and you had correlated short distance errors, and you unfold it, now you have correlated long distance errors. Are they really dangerous or? Yeah.
Well, I mean, I guess there's still constant weights. So I mean, it's not. Hopefully, those correlated errors aren't growing with the code. Like the size of the error is not growing with the code distance.
Right.
So that should be tolerable. Yeah.
All right, cool. Yeah, a lot of interesting questions here. Any other comments or ideas from folks in the audience? Okay, well, I guess if there's nothing else, thanks a lot, Ted, for coming. Really appreciate it. It was a fantastic talk.
Yeah.
Looking forward to seeing neat ways we could explore this. And if you need any help or info from me, just let me know, and I can help track down any data you need.
Okay. Yeah, thanks everyone. This was a lot of fun.